Okay, so we've talked about some interesting cases with varying acceleration, varying force, etc. I want to look at, and obviously the complications are really in the place where these variations are with respect to displacement. And I kind of alluded to at the end of the previous video that there are sections where we look at force that acts in the direction against motion, but it is a function of displacement. I want to take a special case of this, and this section is the last section of the further mechanics curriculum, and it's called Simple Harmonic Motion. They have horizontal and vertical motion, but I want to get to what this whole idea of simple harmonic motion, and I want to take a view to it, maybe different from what a lot of the curricula would advise. But first of all, it's simple in that we're not introducing friction, air resistance, or anything like that. But it's called harmonic motion because it's a specific type of motion. So it's all simple in that we're not going to look at too many dimensions or anything, right? We're just going to do that one horizontal dimension. But it's harmonic in that, and I think it's probably because they found harmony in it, or related to musical instruments because of the wave patterns when natural objects are, you get a little twing on a string, then there's the natural vibration that, and nature seems to want to settle into sine and cosine functions of vibrations. So if you look at it, they're mostly very neat vibrations. So I'm going to take an approach to doing this because this is a specific case of motion. I'm going to start first with a specific case of motion and say, hey, here's my object, and hopefully this color scheme works because I want to try and maybe I don't risk it. Maybe I throw away those light colors and stick with something a little more bright. Okay, so my idea here is there is a line of motion, and an object has a displacement from its center, whatever the center is, and I have an object that is displaced out with some kind of a displacement that now there's, let's say I've pulled it out here, and imagine this to be like a spring or something, or if I was to pull it, when it's let go, there is a varying degree of force that acts on it to bring it back to the center, right? And if this was indeed a spring, then it would come out here, it would return, and then it would go back, get compressed, and come back out. So there's a specific class of motion where that force in the horizontal direction translates to a acceleration that's opposite to motion. This is the direction of the motion. There is an acceleration that's opposite. So obviously when you pass this and you come over here, the motion is on this direction, and then there is an acceleration that's acting against it, so it slows down as it comes here and then picks up speed again as it returns, and then you see this thing moving back and forth. Right, if I take this to be my case, and I now apply the condition that this acceleration is a function of displacement, right? And this is my directional vector of displacement. I'll just say this, call this as x. So acceleration is in that direction, right? Motion is in this direction. What am I effectively doing? I'm bringing this down here to zero acceleration, special case, right? Because displacement is zero in some ways, right? But that doesn't free me from velocity. I'm picking it up from here again, and I'm going back. So there's still this movement, right? This is, sorry, a at x0, a of 0, right? Because that is a function, right? And then the cycle repeats, right? And it keeps going, apparently in what we would discover to be a rather smooth method. But if I just looked at this situation for a moment, I would be able to say that acceleration, which is x double dot, right? Because we know dx by dt x dot and then x double dot is equal to d of x dot by dt. You know all that calculus, so I'm not going to get there. So x double dot here is some function, and for now I'm just going to put a value here called k times x with a negative sign because it's in the opposite direction. So I'm just going to state it like this and leave it here, right? It's a function of x in the opposite direction. So that's, if I just stated it there and defined this to be acceleration, of course I could play with this a little bit and say that, hey, x double dot plus kx equal to 0, second order differential equation, and I can come up with possibly having an imaginary number plus or minus ik to be a likely root of this equation, and then I can also write x in the form of sine and cosine to solve this. But anyway, we'll get there later. So if I wrote that mathematically and then come back to saying what else do I know that has some form of variation, but that variation is repeated, meaning the variation repeats itself in exactly the same manner. And that is where I want to get to. One of the things we talked about, which is circular motion. When we talked about circular motion, we often did a very interesting problem. And this time I'll do the full circle just so you can appreciate it. But what we did is we saw here when we did these, we tried to do some analysis here, and they said for every bit of time that passed, there was less distance covered on the horizontal direction, and then as time came out here, more of the horizontal. So there was some variation in in the velocity, and therefore we assumed there was some acceleration. We tried to resolve it along tangential directions, radial directions. We looked at a few things, but this is a classic case. If you see, and if you continue to have these rotations, you'll see exactly that, where the pattern repeats itself, where you see, in different instances of time, you've covered different distances, and then likewise it reduces here, because when you come back down here, you're following the exact same mode, and then you come back here and it's this part, and then when you go back here, it's a repetition of the same, where you cover for the same instant of time, because angular velocity is constant, angular speed is constant. So if my angular speed is constant, I draw this line here, right? Angular speed, if my angular speed is omega, angular speed times time is theta, so this angle is omega t. Now remember, anything to do with this is not in degrees, yeah? So you're going to kill this. All these are radians. Anything you do on simple harmonic motion should be radians. So set your calculators accordingly. So I know that for that equal time intervals, there was a time interval where I did just this much on the x-axis, and then it increased, and then it increased. For the same angular velocity, my linear velocity along the x-axis changed. So I have some acceleration here. So I want to try and understand that a little bit better. And so I'm going to draw this here and define this, right? And I can say this is A, which can also mean this is the maximum I've gone out from my center. So my center of oscillation, this is the maximum I've drawn myself out is A, right? Call it the maximum movement possible before this, for the cycle to repeat, right? This is also A. We'll complete that circle. Not a very pretty circle, but as long as you know it is. So if I just use this as x-axis, what might be going on here? I've got this as x cosine actually I'm going to use the term, I got to use a pretty A because actually no, I'm using acceleration. I shouldn't say A here because this is confusing, right? I'm just going to say x double dot for acceleration. So I have an A here, pretty A, try to make it pretty, and that would be my x, isn't it? That's my displacement as a function of time. What would be my velocity here? Cosine w theta, angular speed is constant, time varies, so it's like writing cosine n theta is negative n cosine sine theta. So that would mean I have negative A, pretty A, omega I think that looks right. How would I accelerate this object? If velocity can be differentiated again, differential of sine n theta is n cosine theta, so it'll be still negative with negative w again, so it'll be A omega square cosine omega t. Now, I want to take a closer look at this. Negative A omega square cosine, look at that. I think I can write this now pretty conveniently as negative omega square x. And what I think you should remember is this idea of coming up here. So my minus k in a function like this is equal as long as I am maintaining simple harmonic motion. So the criteria that simple harmonic motion is this is the square of the angular of a constant angular velocity. So I can now say that for simple harmonic motion, square is equal to the negative square of angular velocity times x. But I do want to kind of take a little bit of an extension to this. All right, I want to take a little bit of an extension to this. So here I'm assuming if time is equal to 0, right, which means I'm just x is equal to a. So this equation is not really generic in that I'm commencing motion here and analyzing it here. What if motion commenced at this point? Or what if motion commenced here? Right? So I need to be able to build an offset in this equation that allows me to commence motion at any other point. And I think one of the ways to do that is I could potentially, and I'm going to use another color here just to highlight that, I could possibly write that at x is equal to a times, I'm trying to think what's a nice way to build an offset in there. I could possibly do like a cosine omega t plus some constant for the offset. Some constant for the offset, like alpha, which is like an angular offset. Because if my time started here, right? So Wt, if T0 I was starting at 90 degrees, that would be, I could set this up in such a way where this angle, so if alpha was 0, times 0, cosine 0, I'd be starting at A. But if I was starting at the 0 point, at the origin, if my x began here and moved along these directions, I would need an offset. So it's almost like saying I could rewrite this and say for motion beginning at the center of oscillation, right? If I wanted to start at the center, how would I redo the function? I would basically be adding 90 degrees to it, isn't it? Because if I added 90 degrees to this and set it up, could I write this as x is equal to like a sine? So if I just had that and I wanted to do cosine, this is wt, sine of wt plus some alpha. If I reset it like this, what would happen? If time is 0, sine 0 would be 0 with alpha is 0. So I start here. But if time is, so at time 0, I already developed this. It's probably a way of rewriting this. And you'll see why this is valuable, because if I come back here and attempt to solve this equation, I would actually get a possible solution. So you would be able to write this as a plus or minus wi imaginary roots against this equation if I do x double dot, right? Or I could write x in the form of, I think it would be like an a sine, probably omega t. You could probably get this in this form as well. Again, I'll leave it to cosine wt. You could probably write it in this form as well. If the derivative is with respect to time, you can play with the math. But if I now extend this, I can write cosine wt as, it's almost like, because sine is here, isn't it? So I can measure, I can establish, I know that I can write sine of a number plus 90 degrees as its cosine. So if I move, I could possibly set an alpha, which is like a time offset. No, it's an angular velocity offset, because at time 0, now I'm stating that I'm starting my clock here and I'm measuring from here on what's going on. So I'm effectively shifting the position of this wt. So I could write it like this as a possible measure for simple harmonic motion. You could probably evaluate this and say, now I can look at what happens at different angles, and if I'm starting at different times, if I'm starting at this point, then what happens if this point is just cosine wt? If I'm starting at this point at time 0, then I'm just arriving at this value here, because this will become 0. X is basically a, and then sine gets a some value. It's not sine does not become 0 here. You have a magnitude value. I think you can solve for this too. So this is a bit of a tricky area that you need to keep in mind. But fundamentally, if you remember that relationship and how we arrived at it, and that precondition that for simple harmonic motion, this was the establishment. So we got acceleration as a function of displacement, but under simple harmonic motion, for this to be a repeatable, that's why it's harmonic, because it's what nature defaults to. It's the same motion that happens when left its own accord. So you take a string, you pluck it, it has this natural vibration, and which comes up here, which looks really nice. And if you look at that, function, you can just say that a is as far as that string moves up and down, and its frequency with which it kind of goes back and forth is how soon it completes this, which you can get here. How soon is sort of the velocity, right? That function you can derive here if you go to these 2 points, you can say, and I think you'll get angular velocity times 2 divided by pi, which is pi by 2 is 180 degrees. You can see here the sine values, become 0 on each side. So it's the speed with which you go from a positive a to a negative a, right? And if you set your 2x's to that, then what is the time by which you would go? You would kind of redo it, and you would get the sort of the frequency, and then this is what they call the amplitude, right? So this is the fundamental idea of simple harmonic motion. So when they pose problems in simple harmonic motion, your key essence is to make sure that you capture this from this angle. But now let me take this before I go here, and I want to also extend this. And you can do the math here, right? If you develop, or actually let me not use this one. Let me use this equation, because this is the more standard simple harmonic motion equation. But if you extend this further, and you can do the integration, right? Because this is dv by dt. This is dv by dt. That's equal to negative w square x. Notice that in order to do this, you get d here, you get the v, what's dv by dt. Again, because it's x here, you write this as v dv by dx is equal to negative w square x. Dx comes here, you'll square it, you'll get v squared by 2, and then on this side you'll get x squared by 2, and a constant. You'll have to find the constant of proportionality. Once you play with that, you should get a final value of v squared is equal to another. Again, I'm introducing this. You'll get something that looks like v squared is equal to w squared times some value of, say, a. You can write that as square minus x squared. This is another form of motion that you can define. So another area, and you can play with the integration here, c dv by dt, same things that we used in the previous video. Use that concept, and guess what? You will arrive at a velocity equation as well. So the velocity equation is important. That second order differential equation would become very important. The understanding of this is valuable, but knowing how to apply it is more valuable if you know the application. So if the harmonic motion begins, if your time 0 begins you here, then you're going through the cycle here, and you can think about it as Wt becomes pi by 2 at certain amount of time, when time is such that Wt is equal to 90, I should say pi by 2 radians, you return, your a is equal to 0, means, and x is equal to 0. Your x is equal to 0. I shouldn't say a is equal to 0, because a doesn't fundamentally change. It's a constant. Your x is equal to 0, right? And then when time is equal to omega t is equal to, so it's pi by 2 radians, it's pi radians, you're back here, you should be able to get x is equal to negative a. That's the idea here. So you apply that here, you can say if Wt is equal to pi by 2, you can then write t is equal to pi by 2 omega seconds, right? This is seconds. So you establish this value, and then you can say if this is the case, when t is equal to 2 omega, you get this, you see what happens to your equation. The omega cancels out, you get pi by 2, cosine pi by 2 is 1, you'll get, yeah, oh no, did I make a mistake? Cosine pi by 2 is 0, so x is equal to 0, right? So it's an easy one to say, okay, I'm going to use this function very easily when a problem presents to me the fact that, hey, I've extended out to the edge, and now I'm going to return to a point of oscillation. right? So when I'm doing a calculation where time zero is a point where something has been extended long enough, then that's what I get. But if I start with here, what am I dealing with? Now time is zero. I need to start with this and build out. So then I use a sine function, right, with an offset that will give me a value. So basically, that's the fundamental idea, right? Or for example, if I'm not considering motion from here, I'm considering motion from this point onwards. So as time progresses, so at time zero, I need to be x equal to 0. Then I do sine wt, right? Without the offset. That is, the offset is just added to, if I want to go in somewhere. So if I just do sine wt, if my starting point of my calculation for x is here, then at 0, x is 0. And for that, I need to use a sine equation. And that can also relate to this one, because here I have, a complicated case where I'm defining an x where my starting point is somewhere in between, actually a ratio of a by b. If that's my starting point, then I would have an equation like this. So really the tricky part here is to figure out where I bring in the equation. Most problems will be more straightforward, and you will start with a point, where your center of oscillation here and an object is already pulled in. But there may be some cases where they say, hey, there is already an extension, and now calculate, from there. Or they'll say, hey, I'm just adding onto a spring an additional weight from this point. So then you start from here. So your center becomes here, and then as time progresses, you move to A, and then you come back, return from A. So you've got to figure out where you're beginning this. So this is sort of the idea of things to remember when you see anything that appears like simple harmonic motion. Usually the problem will use the term SHM, and you'll see that somewhere. Either they will say SHM, which is typically simple harmonic motion, or you will see a notation like this, or you will see them say that, hey, the motion is defined by that function, right? So they might have different ideas that they will throw in front of you. And again, I added a alpha to these, and I earlier added to this as well. That is only to do a time offset, not so a position offset decides a cosine or sine. So if I start at A, that means the time is 0, x is 0, and I'm calculating my x going backwards. If time is 0, x is 0, I'm here. If I'm starting at the center of oscillation, at time is 0, x is alpha. X is A, amplitude, that's here, right? But if I'm starting somewhere in between, it's a combination of this. But if I add a time offset, then I have a little alpha factor here, which is really to expand the angle, meaning I'm starting off at a different position at a different time, for example. So I'm already not doing t0, I'm doing t at some other time, right? So even right away at time t, I have a value. So at a time t, I have a value here, right? If time was 0, I would still have alpha, meaning I would have something here. So be careful as to how these equations get formulated to you, but fundamentally understand where you want to see motion. Motion has to follow a sine or a cosine wave, and it has to repeat itself. That's the key. If they present it to you as an acceleration problem, understand this and understand the setup of this equation. I encourage you to derive the equation yourself from this, using the dv by dt and this method that we have discussed previously. Arrive at this equation. I think I've got it right, but if I haven't, then you can derive the correct equation. Saves you the effort of memorizing it. But that is basically the idea of simple harmonic motion. And let's extend this idea a little bit more. I'll keep my circle and all those nice things there, but we'll extend this idea just a tad bit more and see where we go in the case of horizontal motion. And if I have in a horizontal motion a spring, right, and I just put in a spring here, and let's say I have an object here, right, and it gets pulled out this way, right, and that's P, and you know that there is acceleration that wants to bring it here, and then it's going to come back and forth, and you can see it dances back and forth. The setup of the equation, right, if you have the spring, I think I alluded to it previously, is tension is equal to lambda times x by L, right? And acceleration acts against it, so that will be negative m times x double dot. So here you can directly see how I've set up that equation to say x double dot is equal to negative. So if you see here, you get the x factored out, and you get lambda divided by ml, a set of constants that now represent here the negative omega square x, right? And that's the relationship. Understand that if this is a spring, and only if it's an elastic spring, or a spring by nature being elastic, that it gets pulled, it would return and then compress. There would be a compression force with a similar equation, right? Because as you compress, T is working in the other direction, same coefficient, modulus of elasticity, and then you would come back out. So this is great to do. You would have oscillation, meaning you would go back and forth. You have SHM oscillation. Right? This is for a spring. But if it was only an elastic string, and if I'd only pulled the string, well, it's going to pull it back, but when it gets to zero, it doesn't have there's no compression. It'll just flow there and just keep moving. You won't have oscillation. You will only have, for a string, elastic string, I should call it elastic string, so inelastic wouldn't work. Elastic string, you would only have SHM, there's no motion until T equals 0. So as soon as the tension is 0, there's no further force acting on it. This equation is not really balanced anymore. So there might be x bar, but x double dot, but x double dot's rapidly coming down to 0 or it just, there's no more force acting. So whatever's the velocity just goes in there and just keeps moving, right? Just keeps, simple harmonic motion is maintained. But after that simple harmonic motion is from this area to this area. After that, it just keeps going. There's no more, there's no additional force to balance, right? So HSM only till what's the right word? Till it becomes slack, till the string becomes slack, right? So as soon as it loses that tension, it becomes slack, and then you don't have simple harmonic motion. Just remember this idea, because they tend to kind of ask you a 1 mark follow-up on a calculation that asks you, hey, what would happen if the spring was replaced by a string? And basically you would just tell them, let them know that that's what happens. Okay, so that's the horizontal view of this problem, right? So we've set it up very easily. Now I want to just take up the vertical motion view, which is the other part that they address, and I'm going to do that by positioning the same. Let me just say I have a spring here, and its natural length, let's say, is L. But as soon as I put a particle on this spring, I cannot use that as my reference basis. There is naturally an inclination of this spring to expand and arrive at another point here, and I'm going to call this as its extension, E. This is the equilibrium position. That's the equilibrium position, which then becomes the center of oscillation. So if I extend the spring and leave it, it's going to go back here, compress, and then come back here. But all of its motion is about an equilibrium position. So then there I can now I can draw an extension x. That's my x. And at that point, I can determine what might be happening. So now there is an acceleration here, m times x bar, right, which is in the negative direction, to a tension, right? What might this tension be? Oh, actually, and there is also, when I'm balanced here, there is the mg, right? This is mg, and this is t. At balance, this is t, right? But when I've come here, there is acceleration. So there's a direction of motion. There is an opposing acceleration. But what else is going on? I have a tension, and I have an mg. Let's just take a look at how we can represent this in a simple form. But when I do tension here, what am I doing? I'm doing tension here as lambda by L, natural length. That's good enough. But what's my extension here? My extension should be x plus e. Right? In my first equation, my mg should be t, which is lambda by L times E. Right? That's how they balance out. But here now I have acceleration acting opposite tension. Right? So there's tension. So can I write this as lambda x by L plus lambda E by L? That's moving this direction, minus what else is going on here? So I have tension on this side. I still have mg. I have mg as a force, mx, and that's a force too. So all of this. Then I have. Let me see if I can get my math right and my directions accurate. So I have mx double dot. Right? That's the net force. That's the net force. Actually, no, that's not the net force. No, that's not the net force. The net force will be tension T minus G. So that's T. So T minus mg. Sorry, T minus mg. So then I would write lambda x by L plus lambda E by L minus mg. Mg is not, these two should cancel out, and I should basically get x double dot is equal to negative lambda by ml of x, which is effectively the same as the one in horizontal. So the function of acceleration has not changed, horizontal or vertical, because the component of g changes. So it tends to act the same way, but the difference is now it gets here. I'm not going to experience zero tension. I still have tension, right? And then I have the oscillation going this way and then brings it back here. So that's the difference, because it keeps extending. But again, notice that this is only for an elastic spring. If I just had a string, I would still check out on equilibrium. I think the math would still check out. But when the string reached the point where it became slack and tension was lost. So if it went all the way back here, suddenly there would be no more compressive force or anything else to push it back. Then it would just be at the mercy of gravity. What would then happen is you only had gravity acting down until you got to a point where tension and gravity balanced, and then so you would have a more complex force. But this would be a classic case where, barring anything else, if it was just a string staying here, extended here, and then further pulled back, would go back all the way, lose its energy, slow down massively, lose that tension force, slow down massively, then fall under the effect of gravity, but this time would be only gravity. There's no thrust force, so it'd be much lesser for it to bring it back here, which then would mean the acceleration would be lower. It would just do this, and you would have it arrive there. It would just kind of nullify, and this you can actually, this is an interesting one, because actually, imitate this. The string imitate is a good imitator of this, because what happens is the amplitude of the wave is reducing, but typically the wave will start converging much faster. I kind of wrote it very, very incorrectly, but as you come closer, it becomes very, very close. And I think that the circular motion is a great way of demonstrating that, because as I spin this around, when the amplitude reduces, it starts spinning really fast. So that math will check out if you do the math and extend the sine function. I think you'll see that as my A reduces, my amplitude reduces, then you will have to get much higher frequencies to much higher WT values in order to get the same X. Yeah, that's an interesting topic here. Okay, but I think that effectively covers the simple harmonic motions extension to horizontal and vertical motions. Again, remember, you get the simple harmonic motion in oscillatory motion for a spring, but for an elastic string, it doesn't. It basically just continues in simple harmonic motion until the string has become slack. Hopefully that covers it. And yeah, again, they don't complicate the problems way too much. The very fact that this is the kind of the end of the curriculum, they don't make it horribly complicated. But I have seen one or two questions where they like to make it a little messy and I tell you that the time that it starts is different, or the spring is, we start capturing at x by 2. So imagine you capture at x by 2. It's almost like coming to this point where this is 45 degrees. So you'd have to play with that angle a little bit. So those are some of the interesting dynamics here. But yeah, that effectively covers or brings us the end of the further mechanics curriculum. I might consider making additional videos if I find some topics that come to my mind that are more sophisticated. But otherwise, I think this area is, if you've got your variable acceleration, variable force concept extremely well covered, this is not a problem. And I do encourage, please derive the equation yourself using x squared is equal to negative omega square x double dot, or second derivative linear equation for x dot double dot equal to negative omega square x. Try to do the integration yourself to establish a velocity function. And if you have the mathematical background, go to attempt the arbitrary solution for x is equal to a sine theta plus b cos theta. Might be worth attempting. But otherwise, I'll leave you with it, and I'll see you in another video. Right, bye.